Okay, so in the previous section, we saw that there were two methods. There was the brute force method, basically for finding the divisors of n, and that was to try the numbers from 1 to n, and then that was method 1. And then the second method was to try from 1 to root n, and then find partners. All right. So we said that the second method was better, but really the question is how much better. So in this little video I wanted to examine exactly how much better it is to examine from 1 to root n versus from 1 to n, and specifically when we're talking about I'm talking about how much better it is for a computer. So what I did was I wrote a little Java program. So if you're familiar with Java, great. If not, I will try to explain this as clearly as I can. The name of my program is n versus root n, because we're comparing if you try all n numbers or if you compare the square root of n numbers, so that's nothing fancy, but that's it. And this is just a function that I created, and the function, what it does is it lists the factors, and that's the name of it right here, list the factors. Don't worry about this if you don't know what it means. It's just stuff that needs to be there. And what numbers am I going to list the factors of? Well, I'm going to list the factors of some integer. That's what int means. Integer n. Okay. So we go down here. What do I do? Well, I want to know how long this takes. So the first thing I did was I stored the time. You can think of this as the start time. Start time. This line right here, I want to record the start time. In other words, I want to figure out when did I start doing this, and then at the end I'll figure out how long when I finished, and then I'll compare the two to see how long it took. So what this says is I'm going to start with number 1. I start with the number 1, and while that number is less than n, I'm going to do this little loop, and then at the end I'm going to add 1 to it to increase it. Okay, so what I do is I check my number 1. I see this is the symbol for what's the remainder. So I find the remainder, and if the remainder is equal to 0, then I print the number, and if the remainder is not equal to number, then I do nothing. And then I add 1, and I go to the next number, and I keep going. And then if you notice here, I didn't go to I didn't say less than or equal to n. I just said less than n, because I know n is a divisor, so rather than put it in my loop just to make it look pretty, that's the only reason. I left it out here, and I printed it after the fact, because I know that it's always going to be a divisor. Anyway, the system.out.print just prints, the system.println just prints the line. Anyway, and then this second one is T1, I got this is the end time. Okay, so then the last thing the program does is it prints out the run time. In other words, how long it took to run is the difference between the end time and the start time, T1 minus T2. Okay, so we'll scroll down here, skip that for the time being. If I let's do a simpler one, for example. Let's let my integer be 12. If I want to list the factors of 12, then a is 12, so I list the factors of a. If I run this, which I just did, you can see that it printed for the factors of 12. We got 1, 2, 3, 4, 6, and 12, and if you check those are correct. And the runtime took 0 milliseconds. Now, it didn't actually take 0 milliseconds. That just means that it took less than 1, and it rounded it off to 0. So we'll do it a couple times, and you'll see that, okay, this time it took 1 millisecond. Most of the time it takes 1 millisecond. Every once in a while we'll get one that takes 0. But for the most part, it's around a millisecond or less than a millisecond to do that. So not terribly long at all. Basically, yeah, not very long at all. Okay, so let's do our number that we just did, which was 2,142. We list all those factors, and we see that that still takes 1 millisecond. Okay, so let's start bumping up our numbers. So if I do, instead of 2,000 is a pretty big number, what if we just did 10,000? What if I wanted to list the factors of 10,000? I hit play, and oh, this took 2 milliseconds. You can see here I have all the factors of 10,000, took 2 milliseconds. What about 100,000? All right, 5 milliseconds. So you can see it's starting to add up the bigger the number gets. Now the other question with though is how does this compare to our other way? So I made another program. This is list factors again, same function, but this time it's list factors root n. In other words, I'm not going to try all the numbers up to n. I'm just going to try the numbers up to square root of n. Now the integer takes the same input, takes a number n, but the first thing I did here is I calculated the square root of n. Now the floor rounds it down, so it's an integer. The int makes sure that it's an integer. Anyway, so that's that. Then I made an array. This is just so that I could get it to print nicely because I wanted it to print in the same order as the other one. So I needed to make an array to store them all, or at least store the higher ones, the ones that were bigger than the square root. I needed to have a counter just to keep track of how many there were for when I printed them. Max index is just to determine in this array how big, how far into the array did I get. But then I basically did the same thing as I did before. Oh, no, sorry. This initializes all of that array to 0 because you have to have something in there. So I just made them all zeros. Anyway, down here you can see this is the exact same thing I had before. Well, very similar. I checked what's the remainder when I divide I by n. Is it, I'm sorry, n by I, is it 0? If it is, then I do this. If not, then I skip it. But you'll see right here is the key thing. I went from I didn't go up to n, I went up to the square root of n. Right. So then down here, what I did was when I find one factor, when I find the small factor, I is a small factor since I started at 1, and all my numbers are less than the square root of n. As I found the small factor, then I had to store, instead of printing right away a small factor, what I did was I stored the big factor. And to find the big factor, all I did was take n divided by I, and that gives me its partner. So I is one number, and then its partner is n divided by I. Okay, great. So then max counter, that maneuvered a little bit just to keep track of some things as we go along. And then if it happened to be a perfect square, I didn't want to print the number twice, so I had to do a little adjustment there. But basically down here, this is where I printed the second half of them. Okay, so we have, and then at the end I stored the end time and again printed out the runtime. Okay, so if we compare these two algorithms, this one is really short, really simple, very sweet. Okay. This one actually turns out to look much longer. Okay, it is. There's a lot more involved. I have to find the square root. I have to find the partners. It's a little bit more involved than just literally trying all the numbers. Does it go in? Yes. Print it. Does it go in? No. Don't print it. So it's definitely a more complicated program. However, in the long run, it's going to turn out to be much more efficient. And we'll see that down here. So what I want to do is I want to do the same thing. So I list the factors of n, but I want to do my other function, which is list factors, what did I call it? I called it list factors root n of a. Okay. Now what this should do is it should list the factors twice, and it does. It says 1, 2, 3, 4, 6, 12. This was for the, down here, this was for trying all of them, and then this one was for trying up to root n. Now you can see that they both took, this one again we said before that the 0 milliseconds is a little bit misleading, but they both take a very short amount of time. If I run it a couple times, that time it took 3, that time they both took 0, so it's sort of all over the place here. But a relatively short amount of time. Now, if I bump up the number, if I make this 1,000, all right, then both of them again take a pretty short amount of time. to make it 10,000. Here we have 0 time for the 0 time for, or 0 milliseconds, so it's still taking a really short amount of time, and 1 for our other one. If we bump up to, let's see here, that's a million. If we bump up to a million, this one took 37 milliseconds, and then the other one took 2 milliseconds. Again, 37 milliseconds is still not very long, but anyway, let's keep going. If I had let's add 3 more zeros, which is a billion. So that's 1,000, million, billion. Okay, a billion, and that's about the max of what I can do. So here it's going. It's listing the factors of a billion just by trying all of them. And you can see it's actually still thinking. There it took 6,837 milliseconds, which is about 7 seconds. Whereas the second algorithm, using the square root, only took 4 milliseconds. You can see how quickly it popped up. Huge advantage. Now I have this summarized in a little bit of a table here. So if we do n versus root n for 1,000, this was from an app. I found an app online which would do these calculations for you, but I wanted to write the program too. But anyway, just so we have this, we see actually root n takes a little bit longer, and that's probably because of the extra overhead as far as the determining the square root, storing the values, that kind of thing. So for a short number, it's actually, for a small number like 1,000, the just brute force way of doing this is a little bit better. But as we get bigger, you can see that, well, in this case actually, it's still 10,000 still doesn't show much advantage for root n. Well, it doesn't show any advantage actually. Root n is still losing. But as soon as we get up to 100,000, now finally root n is slightly faster. Now, is that significant at all? No, not at all. But it's slightly faster. Now, if we get up to, if we skip from 100,000 to 100 million, we got 7 seconds. This is comparable to what we saw for the program that I wrote, but this is still less than less than a second, but it's also less than a tenth of a second. 92 milliseconds. Anyway, if we go here to a billion, that should take, for whatever program, anyway, for this app, according to this app, whatever processor it was using, it should take 78 seconds, and then this one is still less than a second. Matter of fact, it's less than a quarter of a second. If we get up to, let's see here, 1, 2, 3, 4, 6, 7, 8, 9, 10 zeros. Now this actually is beyond what you can store as an integer. But you can store this as a long, so it's very easy to have numbers this big in your computer. And if you try to do this with square root of n, try and factor it, you will get all the divisors in just over a quarter of a second. If you try and do it by trying every single number up to n, it will take you almost 2,000 seconds. 2,000 seconds is a significant amount of time. So here we go, 10 to the 18th. I picked 10 to the 18th because 10 to the 18th is about the biggest number that you can store, biggest integer that you can store easily. I mean, you can store any number if you're creative enough about it, but easily in a computer program, 10 to the 18th is about the biggest number that you can store. If you wanted to find all of the numbers, all of the divisors of that number, using square root of n as your number of trials, it would take about 4 minutes. So that's not an insignificant amount of time. That's a long time, especially for a computer. We hate to wait 2 seconds for our web pages to open up. But on the other hand, 10 to the 18th is an astronomically large number. As far as n goes, this would take you about 2,000 years. So waiting 4 minutes is annoying. Waiting 2,000 years would be the end of you. So subtle changes like that, as far as computer programming can go, can have a huge impact on your algorithm.